Hello there, and welcome back. Today we're going to continue our exploration of derivatives and focus on an application of what is known as finite difference approximations for finding the value of the derivative, second derivative, or even the 87th derivative of a function at a point as long as you're willing to lose the exact accuracy for which the algebraic representations of derivatives generate. So as we already know, the derivative of a function f is commonly derived or defined as the limit as epsilon goes to 0 of f of x plus epsilon minus f of x over epsilon. This is often referred to as the forward difference definition of the derivative. But obviously, if somebody says, well, why do you call it the forward difference definition of the derivative when that's technically the only derivative? Well, actually, you can define the derivative of a function in a few other ways. So if you think about what this formula represents, so we have some function, and we're trying to find the slope of this tangent line. And if you remember where this, this representation came from, we pick a point in the future of x, in particular x plus epsilon away, and we find the slope of that secant line, or that average rate of change value, and we make epsilon get closer and closer to 0 from the right-hand side, and that generates what we call the derivative of the function at that point. But you don't have to choose a point in the future. You could technically choose a point in the past. So an alternative and equivalent way of finding the derivative of a function is via the representation, the limit as epsilon approaches 0, of, and again, you can derive this from the average rate of change formula, just going the behind x. So x is going to be the future of the value in the past. So it's going to be f of x minus epsilon divided by x minus epsilon, which is still equal to epsilon. So this representation is known as the backward difference definition of the derivative. And what this does is it looks at a curve, and again, we're interested in finding the value of the derivative at a point x. Now we're going to choose a point in the past of x called x plus epsilon, and we're going to find the slope of that tangent line, and we're going to send that distance between x minus epsilon and x, which is obviously still epsilon, and we're still going to get closer to 0, and that's still going to be approaching the same slope tangent line. And you could ask, well, is there any other ways you could define the derivative? Yes, there's actually infinitely many ways one could do so. The other one that I'm going to introduce today is the following, which is to some degree the average of the forward and backwards difference. So if you take the average of these two, you're going to have f of x plus epsilon minus f of x minus epsilon divided by 2 epsilon. Right? So you actually don't need to know what's going on at x in order to find the central difference value. You just look in the future, look in the past, and then sort of find the average of how those two are sort of changing each other, and that's what we refer to as the central difference. Central difference definition. Right? So sometimes to distinguish between them, sometimes we will put a superscript before the derivative operator. For example, we can say that this is the forward difference definition, this is the backwards difference definition, and this is the central difference definition. But is it possible that these operators on a function produce different values? So I'm going to state a particular theorem that addresses this question. So if f is differentiable at a point x equals a, which should belong to the domain of some function f, then the derivative at x is equal to a of the function, regardless of the derivative approach, forward, backward, or central, are all going to be equal to each other. Now, in case you don't know what we mean by differentiable at a point, it needs to be what we say loosely well behaved. For example, you cannot have a corner at that point, for example, like absolute value of x. You cannot have a cusp at a point, like x to the 2/3. You can't have any removable discontinuities at a point, any jump discontinuities at that point, no infinite discontinuities at that point, and the function must exist to the left and to the right of that point, right? So as long as you do not fall into one of these categories, in most scenarios, we say that f is differentiable at that point A, and one can show that these derivative definitions all produce the same value, assuming that, again, it is differentiable there. Now, one can say, well, okay, those are just different rules for finding the derivatives. What does that have anything to do with approximations? So typically, we cannot take the limit as epsilon goes to 0 in practice, right? So what we do is we remove these limits, and now what we have is forward, backward, and central difference approximations, where the accuracy of those approximations are dictated by how small epsilon is chosen to be. So typically epsilon is a positive number, but arbitrarily small. So obviously the smaller the better in terms of accuracy, but generally speaking, these are what we call forward, backward, and central difference approximations, and one can also show that the central difference approximations on average provides better results than the forward or backward. Not always, but on average, better approximations, given the same epsilon for each of these three processes. Let's go through an example. So let's assume we have this function defined to be equal to e to the power x divided by 2 plus sine x. So you should already know that sine of x is always between -1 and 1. Therefore, this 2 plus sine of x is never going to be equal to 0, provided that x is a real number. Therefore, this function has a domain of all real numbers, or it can be chosen to be the set of all real numbers. And generally speaking, this function doesn't appear to have any weirdness to it in terms of differentiability issues. So one can say, well, how is the function behaving at x is equal to 2? Is it increasing? Is it decreasing? Does it have a max or minimum value there? What's going on there, right? So one could ask, in particular, find the derivative of that function when x is equal to 2. Now, up to this point, at least in this series, we have not discussed how to find the exact derivative of this function, but eventually we will. But generally speaking, there could be other arbitrary functions that you don't know how to find the derivative of. So if you can't find the derivative of a function at a particular point, the next best thing we have in front of us is to approximate the derivative at a particular point. And regardless of what that function is, you can always use finite difference approximations to approximate that derivative up to whatever degree of accuracy that you desire, because you choose what that epsilon is equal to, and obviously the smaller the epsilon, the better. So what we're going to be choosing is, just for demonstration purposes, to be equal to 0.01 for our epsilon value. So how do we do a forward difference approximation for this derivative? So that's going to be equal to, so a forward difference approximation at x is equal to 2 for this particular function, so we're going to be calling this function f of x. That's going to be approximately equal to f of 2 plus epsilon minus f of 2 all divided by our epsilon value. So obviously we can plug in 2 and 2 plus 0.01 into this function and get some value back. So you can find, for example, that f of 2 is approximately equal to 1.9886, and f of 2 plus epsilon is approximately equal to 1.9975. So from these two values, you can find that this finite difference approximation is approximately equal to 1.9975 minus 1.9886. So that's obviously going to be a positive difference. So we have evidence to believe that this function is increasing there. Divided by our chosen epsilon value, make sure you keep that consistent. And that's going to be approximately equal to 0.8845. So that's the approximation to the derivative at this point. And you may be like, well, I'm not exactly sure if I should trust the forward difference approximation. Let's do the backwards difference and the central difference just to compare. So again, the backwards difference approximation at x is equal to 2 for this function f is going to be approximately equal to, so that's going to be f of 2 minus f of 2 minus epsilon, all divided by epsilon, and you can find that that's going to be approximately equal to 0.8738. Obviously there is some difference between them, but one can be at least numerically sort of sure that the derivative, at least to one decimal place, should be about 0.8. So, again, on average, the central difference approximation usually is more accurate than the forward and backwards difference. You can find it directly, or one could take the average of these two. But the central difference approximation, x is equal to 2 for this function, is going to be approximately equal to f of 2 plus epsilon minus f of 2 minus epsilon divided by 2 epsilon. So evaluate 2 plus epsilon for your function, 2 minus epsilon for your function, subtract, divide by 2 times epsilon, so 0.02, and that's going to be approximately 0.8791. And again, on average, central difference approximations are usually more accurate, provided that the function is well behaved. So one can say that the derivative of this function is about equal to 0.87, 0.88, but nonetheless, one should be sort of convinced that this function is increasing when x is equal to 2. So next natural question that you may want to ask is it possible to approximate higher order derivatives, like the second, the third, the 50th, the 1763rd derivative at a particular point? The answer is, of course, yes. So one can, of course, ask, well, if I can find the derivative of this function, why can't I just find the exact value? So derivatives will give you the derivative, or the derivative function can give you the derivative value at any point in its domain. But if you're just interested in one point, sometimes it's a little bit algebraically overkill to find the 50th derivative of a function everywhere when you're actually just interested in one point, which is where this finite difference method actually has their advantage. So let's see if we can find a finite difference method representation for, the 20th derivative or something like that. So obviously we're going to start with a derivative approximation. So we know that the first derivative of a function is defined to be equal to the limit as epsilon approaches 0. Let's assume we go about this in the forward way. So that's going to be f of x minus epsilon minus f of x divided by epsilon. And I'm going to assume by default that this is going to be forward. You could also, of course, do this for backward or central, but I'm just going to show you the forward one just to keep things nice, right? Because we can control our epsilon to be super small, but you could, of course, derive a similar backwards or central difference representation for these. So what would the limit definition be for the second derivative of a function? So that's just going to be the derivative of the derivative. So that's going to be the limit as epsilon goes to 0 of f prime of x plus epsilon minus f prime x all divided by epsilon. And then we can apply the forward difference definition for the derivative of both of these functions. And let's assume that those limits are also in terms of epsilon as well. So that's going to be equal to the double limit as epsilon goes to 0 of, so that first derivative is going to turn into f of x plus 2 epsilon minus f of x plus epsilon all divided by epsilon, and then minus f of x plus epsilon minus f of x all divided by epsilon all divided by that lonely little epsilon that used to be there. So that's going to give us the limit as epsilon goes to 0 of, we're going to have 1 divided by epsilon squared times f of x plus 2 epsilon minus 2 f of x plus epsilon plus f of x, right? So that is the forward difference definition for the limit of a derivative. So one can say, well, can you do it for the third? Of course, do it again. So you may want to pause this video to try this on your own to see if you can get it, but one will find that the forward difference representation for the derivative will be equal to the limit as epsilon goes to 0 of 1 divided by epsilon cubed of f of x plus 3 epsilon minus 3 f of x plus 2 epsilon plus 3 f of x plus 1 epsilon and then minus f of x plus 0 epsilon. And that's going to be that. So the first thing you should obviously be able to see is that these signs are alternating, plus, minus, plus, minus, plus, minus, and so on. But what about their values? For example, notice we have 1, 3, 3, and 1. One can show that those are actually binomial coefficients. So if you don't remember binomial coefficients, remember c and k is going to be equal to n factorial, k factorial, n minus k factorial. So for example, this is going to be 3 choose 0. This is going to be 3 choose 1. This is going to be 3 choose 2. And 1 is going to be 3 choose 3. Right? So this is again to give you the coefficients of that expansion. So if you want to extend this to the general term, and indeed you can. So if n is a natural number, then the nth derivative of f via the forward difference method can be found by the limit as epsilon goes to 0 of 1 divided by epsilon to the power of n times the summation from k is equal to 0 to n. So that's our alternating term. Those are our coefficients, c and k. And then f of x plus, notice we're 3, 2, 1, and 0. So it's decreasing, not increasing. So it's not from, x plus 0, x plus 1. It's x plus 3, 2, 1, down to 0. So n epsilon, n minus 1 epsilon, n minus 2 epsilon, all the way down to n minus n epsilon, right? So that's going to be equal to x plus n minus k epsilon, where your function is going to be evaluated. And that is the forward difference representation of the nth derivative of a function, where obviously n is a natural number. Let's do an example. So let's assume we have again this function e to the power x divided by 2 plus sine x. Even if you knew how to do the first derivative of this function, once you get that result, you'll realize that finding the derivative of that function is extremely very intensive, and then the derivative of that, and then another derivative on top of that can be very, very algebraically annoying. So let's assume that we want to find the fourth derivative of this function when x is equal to 2, and let's assume that we are willing to work with an epsilon value of 0.01 with a forward finite difference approximation to this value. So what would the forward difference representation for the fourth derivative at 2 look like? So the fourth derivative evaluated at 2 of this function, let's give it a name, let's call it f of x. This is going to be equal to 1 divided by epsilon to the power of 4, and again this is an approximation of f of 2 plus 4 epsilon. So our coefficients for 4 are going to be 1, 4, 6, 4, 1 if you do your C4 k's. So k is equal to 0, 1, 2, 3, and 4. So 1, 4, 6, 4, 1. Again, it's going to alternate as usual. So it's going to be minus 4 times f of 2 plus 3 epsilon, and then plus 6 times f of 2 plus 2 epsilon, minus 4 times f of 2 plus 1 epsilon, and then plus f of 2 plus 0 epsilon. So that's going to be the full expansion. So that's going to be equal to 1 divided by epsilon to the power of 4, right? Now that, keep in mind, epsilon to the power of 4 is going to be very small. That means 1 divided by epsilon to the power of 4 is going to be very large, right? So you need to make sure that your computer or your calculator has the computational capacity to handle the precision of these calculations, especially the smaller and smaller your epsilon becomes, which is why try to stay around 0.01, 0.001, just for basic approximations, right? Because you need more computational availability to handle more precision. But that's going to come out to approximately, again, 1 divided by epsilon to the power of 4. If you do 2 plus 4 epsilon, that's going to come out to approximately 2.025, and you're going to have minus 4 times, and if you evaluate 2 plus 3 epsilon for our function, that's going to come out to about 2.016, and that's going to alternate plus or minus for all of those terms. And you can find that this is actually going to come out to approximately 4.2764. So we have evidence to believe that the fourth derivative at x is equal to 2 for this crazy looking function is about 4.28, and you can interpret that however you may if you have an interpretation in your mind of what the fourth derivative represents. Now, one, of course, needs to keep in mind that this is not the exact answer. Actually, one can find that the fourth derivative evaluated at 2, which is sometimes represented as this, or some people will write it in terms of prime, so 1, 2, 3, 4, and 2, and some people will also write this as the fourth derivative of f of x evaluated at x is equal to 2, all those are equivalent notations in this context, is actually about 4.0627. That's approximately the exact answer, right? And if you compare these two, you're going to be like, well, at least it's accurate to the nearest integer, and you would be right when you say that. But if you need more decimal precision, obviously an epsilon of 0.01 is not good enough, right? So obviously you need to do those things blindly, because this we technically do not know what it is, because if we did, we wouldn't have to approximate it. So just keep a couple things in mind. For example, if you want more accuracy, you need to make epsilon a little bit smaller. Another thing you could do is, instead of using the forward difference, you can use a central difference approximation instead of a forward, because on average, again, that's a little bit more accurate. There are other methods aside from these finite difference approximations, but we won't get into them there because we do have complete control over the epsilon, provided that you have the computational tools to handle it. So up to this point, regardless of what the function is, even if you do not know the algebraic rules to find the derivative, you can always approximate any order derivative to any order accuracy that you want, provided that you can actually work through these little calculations with precision. Hope you enjoyed, and I'll see you in the next video. Take care.